So we're live right now?
Now we are live, yes.
We have to go.
All right, so our lesson today is going to be on velocity and other rates of change. And I'm going to insert a page so we can talk about some concepts before we get started. And so the title of this one is going to be Motion. Because Newton, believe it or not, discovered calculus in order to solve physics problems. And physics problems he was trying to solve involved motion. Okay, and the first function we're going to talk about is the position function. And in calculus, position sometimes is called s of t, versus in physics, it's called x of t or y of t, based on which direction you're going. And we're going to, for the sake of discussion, we're going to say that this is going to be in meters. So those are the units. Okay? Now, if I have some sort of position graph, and here it is, where I have s of t, and my y-axis is in time. This will be seconds, and then this will be in meters on the y-axis, right? So you got the x-axis is in time, and the y-axis is in position or meters. If I were to take the derivative, or the instantaneous rate of change of that position function, that's nothing more than the slope of the tangent line to the position function. And the slope of the tangent line, if I were going to talk about it, has a slope of rise over run, and the rise is in what units? Meters. And the run is in seconds. So the slope of the tangent line, its units will be meters per second. Well, meters per second, we all are familiar with, I hope, is velocity. Okay? So the first derivative velocity is equal to the first derivative of the position function. And its units will be meters per second. Now this is the instantaneous velocity. And what do I mean by that? Instantaneous. Yep.
It's the velocity at a given moment.
At a given moment in time. That's right. Well, the velocity will have its own derivative. And so let's do a really quick velocity graph here, and I'll try to keep it true. All these slopes appear to be positive. And an increase, I mean, this is big positive. Big positive. And it's slowing down a little bit, and then I don't even know if I have a zero slope, do I? Anyway, I'm just going to say that's the velocity graph for now. Just bear with it. Now, does this graph have tangent lines to it? We can find the instantaneous rate of change of the velocity, and that would be its tangent line. Now, the velocity units on the y-axis would be meters per second, and on the x-axis it would be in seconds. So if I were doing something similar and try to find out what the units were for the slope of its tangent line, it would be meters per second in the rise, and then seconds in the run. So that slope would be meters per second, which is acceleration, that's right. So acceleration is equal to the first derivative of velocity and the second derivative of position, and that'll be meters per second squared. Well, the acceleration is a curve in its own right. I should have just done a cubic, a quadratic, a line, right? But it is, I was too, probably crazy this morning. All right, so this has a zero slope where? Right here. And maybe a zero slope here. And we got negative slopes until we get a zero slope, and we're still positive. So I'm going to say maybe that's the acceleration graph. And this is time, and this is in seconds still. This is going to be in meters per second squared. And if I'm considering the slope of the tangent line to this function, the tangent line slope is going to have what units? Meters per second squared. And the run will be seconds. And then that slope, or instantaneous rate of change of the acceleration, is going to be what we call jerk. Which turns out to be the first derivative of acceleration. You know where I'm going, right? The second derivative of velocity. And then the third derivative of position. And its units are going to be meters per second cubed. And remember, the last time we talked about jerk, that's the feeling that you get when you're riding a roller coaster and you're accelerating, and all of a sudden, what happens? The acceleration changes. And what happens to your head? It jerks back, right? So that's why they refer to that as jerk. All of these measures, or all of these functions, velocity, acceleration, and jerk, are instantaneous rates of change. I'm making a big distinction because if I were to ask you now, what is the average velocity over a time interval? Is that instantaneous anymore? That's average. And average requires 2 points in time. So let's talk about the difference. Average velocity over the interval T1 to T2. Now, in math, when we talk about averages before we get to calculus, what do we think we're doing? We're adding two things and dividing by how many things there are. Okay? Well, average velocity is just your change in position over your change in time. And so in math language, that's going to be delta S over delta T. Now, what's missing from that little equation on the right, or the expression on the right? It's delta S, isn't it? It's not delta V, is it? Now, why do you suppose it's delta S instead of delta V? What are the units of delta V? Meters per second over seconds would give you acceleration. So when we are trying to find average velocity, do not touch the velocity function, which is what a lot of folks miss. We need something that's meters over seconds, don't we? So if it's meters over seconds, that means it's the change in position over the change in time, which is nothing more than a slope, right? We know we say dy over dx to find the slope. So this would equal s of time 2 minus s of time 1 all over time 2 minus time 1. And that's the slope of the secant line to the position function between those two times. Does that make sense to everybody? So average rate of change is over an interval. You don't use velocity when you do that. right, the next thing we're gonna talk about is. I'm on air, I'm live. Of course, someone comes to the door, right? Average velocity is meters per second. Let's talk about average acceleration. Well, average acceleration is also going to be over a time interval from time 1 to time 2. And just like velocity, we're not going to touch the acceleration function. What are we going to do? We're going to do delta. Yes, delta V over delta T. And that would then be V of T2 minus V of T1 all over T2 minus T1. Now let's look at the units and see if the units work. The velocity is in what kind of units? Meters per second over seconds. Does that give us acceleration? Yes, it sure does. So that's definitely acceleration. And then the last one's going to be average jerk. And if you're going to talk about jerk, you may as well not be average about it, right? I'm kidding. Okay, here we go. This is going to be over another time interval. So what do you suppose that's going to be? Delta A over delta T, which would be A of T2 minus A of T1 all over T2 minus T1. And let's think about those units. That's going to be meters per second squared over seconds, which is meters per second cubed, which is jerk. Yes, ma'am. So the question is, are you guys going to remember that the velocity, acceleration, and the jerk functions above are instantaneous rates of change? That's at a moment in time. And then the average is over an interval. And if you're talking average velocity, are you touching the velocity function? No. If you're talking average acceleration, are you touching the acceleration function? No. One other thing I'd like to point out, what is delta S mathematically? Change in position. What do we call that in physics? Displacement. Oh my gosh, we have a physics word in calculus. All right. I can say it online. Good job. All right, here we go. Delta S is displacement. It's good to know, right? So all this talk about motion, how do we know when something or a particle or a body is stopped? When the velocity is equal to 0. So in calculus, when we talk about trying to find out when a body is stopped, what are we going to do? We're going to take the velocity function and set it equal to 0. And that would also be your justification. Because if you have no velocity, you aren't moving. You're going 0 meters per second. Or feet per second. Or whatever unit you're in. Now for convention, in this class, in our Q2B motion, if our body is moving right, or up, we're going to suggest or have the velocity be positive. And if a body is moving left or down, our velocity will be not all at once negative. And in calculus, this is how you're gonna justify your answer. If somebody were to ask you, find the intervals where the particle is moving right, you could say, well, the particle is moving right from -infinity to 2 since the velocity is greater than 0. That's how you're gonna justify your answer, okay? A body is slowing down. Now let's have a discussion here. I'm gonna draw a picture of our baseball, right? We have to have, there's our baseball. We're gonna throw it up in the air. Okay, here it is. I'm throwing it up in the air. What happens? It goes to a point and then it comes back down. So what's happening when you throw the ball in the air? Are you giving it some velocity? You are. And the velocity you're giving it is what sign if it's going up? Positive. But what happens the second you release it from your hand to the velocity? Well, is it slowing down? I guess is my question.
Yes.
It's slowing down. So everybody agrees that the ball is slowing down on the way up. And the velocity we said was greater than 0, but the acceleration due to gravity, as I heard you all say, is less than 0. It's negative. They're working against each other, aren't they? So if the velocity and the acceleration are working against each other, then what happens? You're slowing down. And then for a moment in time, what happens at the top here? The velocity is, and I'll put a little dot here, is equal to 0, which means it stops for just a moment. And then what happens to the ball? It starts
Accelerating downwards.
Well, it's always accelerating down, right? You see the acceleration is always negative. The velocity is now negative because velocity is a vector and a velocity has magnitude and direction. And so now it's going down, but it's speeding up. Why? Because the velocity is now less than 0 and so is the acceleration, and they're working together. And when the velocity and the acceleration work together, you're speeding up, regardless of which direction you're in. Okay, so body is slowing down then when B of t and A of t are not working together, which means they have opposite signs. A body is speeding up when V of t and A of t have the same signs. So is it enough to know what the acceleration is? No, you have to compare the acceleration and the velocity's directions in order to know if they are working together or working against each other. All right? So those are my one-page notes on motion. So let's do some problems. All right, so this is what we might be seeing. Now, in this class, like I said, we're going to have two-dimensional motion. We're going to go right, left, or up, down. We're not going to be moving in free space. That's for multivariable. Okay, and so I've got some examples of what you might see in the homework and on the AP exam and the notes here that follow. So I'm going to give you some graphs and we're going to discuss their relationship here. So the graph below shows the position of a particle moving along a horizontal coordinate axis. Graph the particle's velocity and speed. Now, I haven't talked about speed yet, but speed is a scalar quantity. Velocity is this is a vector. What do I mean by vector? A vector has direction and magnitude. Guys are so smart. Oh, I'm sorry. Yeah, I know. And so speed is the absolute value of velocity. And so it's just the magnitude piece, isn't it? And speed is a scalar. It is directionless. So if someone is asking you how fast you're going, do they care which direction you're going? No, so that's a speed question versus a velocity question. All right, but they've asked us to graph the velocity first. So the velocity, what is the relationship between position and velocity? Graphically. If we go back to our initial discussion, we said that the position function had tangent lines to it, and the tangent line slopes were velocity, right? They were meters per second. So the slopes of the position function are going to be the y values of the velocity function. So what is the slope? Here from 0 to, I don't even know what number that is. 1, 2, 3, 4, 5, 6, 7, 8, 9. 0 to 9. Oh, no, 0 to 7. 1, 2, 3, 4, 5, 6, 7. It's 0. Now, when we take derivatives, we have to watch out for things, don't we? What are the 4 things we have to watch out for? Corners, cusps, vertical tangent, and discontinuities. Listen. All right? Do you see any of those in this graph? Yowza, I do. We see some corners, don't we? So I'm going to have open dots on the derivative, which is the velocity graph, where I have corners. So I have a 0 slope from 0 to 7. So and I can have a solid dot here, because is this a corner here? No. And I'm going to go 1, 2, 3, 4, 5, 6, 7 with an open dot here, and there is my first part of the velocity graph. I hope that makes sense, because the position is saying I'm at 3 until 7. Does that mean I'm not moving? Yeah, it means I'm not moving. All right, and now we need the slope from 7 to 11. Okay, so what is that slope? It looks like we're going -3 over 2, which is negative 1.5 roughly. So we're going to put an open dot here. This is 7, 8, 9, 11, and open dot. And why am I using open dots on these two? Because I have corners going on. That's right, I can't take the derivative there. The slope from the left is not equal to the slope from the right. All right, now what is the slope from 11 on? 2, hold on, this is 11, 12, 13, 14, 15, 16, 17, 18. It's 0. Everybody, oh, no, it's not 0. I'm sorry, it's not 0. What is it?
It's 1.
From 11 to 12. What is it? Is that 6?
Yes.
6. Sorry, I had a brain fart there. 1, 2, 3, 4, 5. Oops. Helps to have some aid. Open dot. That's really skinny, but there it is. And then I have a 0 slope from 12 to 18. And then I have a slope of 1. Good. Till the end. And I can have a solid dot at the end because I don't have a corner there. And that's the velocity. All right, now our charge is to graph the speed. So what's the difference going to be?
Then negative 1.
The negative 1 down here is going to be moved up. Okay, so we're going to just reproduce this from 0 to 7. Open dot. And then we're going to go to 1.5 above here. To 11. There it is. That's open. That looks closed, but it's really open. And then we're going to go back up to 6. No, that's open too. My ink is too thick. And then we go down to 0 until 18. And then we're going to go back to 1 until the end again. And that's the speed. Okay, so the only thing different was we took the negative velocity and forced it to be positive. Questions on how to do that? Yes.
For the, you have like that first one that has a closed circle and a open circle at that spot, and then on the right it doesn't. What's the difference between those two corners?
Is this a corner? Right here?
No, the next one.
This is a corner.
And then you have a closed circle.
And this is
Oh, that's open?
all of these are
Oh,
open
that
on the
looked closed to
inside.
me, that's why I was confused.
Yeah, no, it's open.
That left one looked closed.
Yeah.
Okay, well then.
I'll try to make it look even. It's my ink is so thick,
That's
You
my
know?
bad.
okay? That's a good question. All right, let's see how we can answer these questions down here at the bottom. It says, when is the particle moving to the left? Now, how do we know a particle is moving to the left, Haley? So when the velocity is less than 0, which occurs between 7 and 11. So we can say 7 to 11 since, how do we know? V of t is less than 0. When is the particle moving to the right?
Everywhere.
From, this was 18. This is 18, 19, 20, 21, 22, 22.
And the little 6.
Oh, the 6 too, right.
So it's 11.
So we're gonna say from 11 to 12? That's right. Thank you for reminding me of that. It's easy to overlook that little bitty positivity there, okay? Now, you do not have to use a union symbol here because it's just asking when. So I'm gonna say 11 to 12 and 18 to 22, and then I'm gonna say, how did you know? Since? This is therefore, no, that's since, I'm using the since, that's right. Velocity is greater than 0. And then when is the particle standing still? 0 to 7, 12 to 18. Yeah.
19 to 22.
Yeah, I thought, well, whatever the graph says, yes. I'm using 18 on mine, so if you use 19 on yours, that's fine. Okay, yeah,
Is it the bracket
let's talk about that. Where?
for the particle standing still?
Where would you,
Put a bracket at 0.
okay, you can put a bracket there, but I don't know what it was doing before then, do you know what I'm saying? Sure, we can put a bracket there. I would accept either. Well, I'm sorry, when the particle's standing still, is the particle standing still? Yes, it is. Yeah, I'd accept either. Some books will leave it open, some books will leave it closed, but anyway, so how do we know? Did I get all of those locations? Since V of t is equal to 0. When is the particle moving the fastest? Now that's asking when the speed is the highest. So that's going to be between 11 and 12. You know, I would probably say since speed has a max at this point. Okay, so let's go on to the next one. Since I did one just like this, I'm gonna skip number 2 and move on to number 3, if that's all right with you, because this one's different. That one was pretty much the same. And on a day when we don't have mass, I will be able to do that. A searchlight is shining along a straight wall of a prison. Positive vision, isn't it? A graph of the velocity of the light, v of t, at 3-second intervals of the time is shown in the graph as well as a table of values. Okay, so this is feet per second versus second. So this is what kind of graph? It's a velocity. This is a velocity graph, but its slopes are acceleration. Okay, so I like to put it in big letters so that I remember what I'm looking at. So this says at what interval for part A, at what interval of times is the acceleration of the searchlight positive? It's when the slopes are positive. Well, when are the slopes positive? Okay, so we can say from 0 to 12. And what else? Good, 18, 21, I like it. 24 to 30. And how do we know that? What's it?
The slope or the line, so I can go in the positive.
When the velocity is doing what? It's increasing, but can I say that, what is the slope to this? It's going to be v prime of t is which equals a of t, right? Is greater than 0. I'm saying, when I say v prime of t, what am I saying? I'm saying the slopes are greater than 0. They're positive. Everybody agree? Okay? So find the average acceleration of the searchlight over the interval 9 to 27. So this looks like I need average acceleration. Am I touching the acceleration? No. So I'm going to say average acceleration from 9 to 27. It's going to be what? It's going to be delta V over delta T, which is going to equal V of 27 minus, good, V of 9, the velocity at 9, oops, I got V 9, over 27 minus 9. So the velocity of 27 looks like it's, if I look at my chart here, it's going to be 0 minus at 9, 2 over 18. So that's negative 1/9. And what are the units here? Meters per second squared. No, feet per second squared, right? Because that's a problem. It's feet. That's not too difficult, is it? No. Just got to pay attention. If it's average, you're not touching the acceleration. Okay. Give an approximation for the acceleration of the searchlight at t equals 15. Now that's just a moment in time, isn't it? So I'm going to say acceleration at 15 is approximately, because it said approximation. Now, I have the velocity at 15 seconds, but I do not have the acceleration. But could I approximate it? You see at 15, now I have a pretty reasonably straight line here. Yes? So could I use some points around it to approximate? So I could say, I could use the secant line between 18 and 12, do you think? So we could say that's approximately v of 18 minus v of 12 all over 18 minus 12. So that's an approximation, isn't it? Could I use different points? Sure. This is an estimation, it's an approximation. So as long as you show what point you used and it's reasonable, nobody can fault you for that. So there might be multiple answers here. So let's do, what's v of 18? It says -7. Minus v of 12. What? It's 4? Okay, I should trust you guys, sorry. Over 6. So this is -11 over 6 feet per second squared. Now, did I expect a negative answer here? Yes, because the slope is negative. Good. And those of you that have to go for math can go. I mean, I don't want you to be afraid to go. For what values of t is the searchlight speeding up on the wall? Oh, speeding up means the velocity and the acceleration are working together.
Oh.
That's going to occur when the velocity is positive, the acceleration is positive. Or the velocity is negative and the acceleration is negative. Okay, so what I like to do is a sign chart. SIGN chart. So this is the velocity. And I'm just gonna do a little sign chart here. The velocity is negative until it's 6. Do you agree? Yes? And then it's 0. And then it's 0 again, and this is 15. And then it's 0 again at 27. And then it ends at 30 here. So then it's positive in this interval, it's negative in this interval, and then it's positive again in this interval. Everybody agree? What I love about sign charts is now I can say my particle's moving left, right, left, and then right again, can't I? I can read it right off of there. I don't even have to worry about how getting lost in what this graph looks like. I can say it's moving left, it stopped, move right, stop, move left, and then it stopped and moved right again. Which is kind of cool. You can do that. All right, now let's do the acceleration sign chart. Now, what is acceleration with respect to velocity? It's the slope. So the first thing I want to plot are 0 slopes to this velocity graph. So when do those occur? Oh, good. Yes, you're right. And the first one is 12. You're absolutely right. 12, I have a 0 slope. 18, I have a 0 slope. Good. 21. Goodness gracious, I got a whole bunch of them. And then 24. Make it a thinner pen. So what kind of slopes do I have between 0 and 12? Positive, good. There's my sign chart piece. What kind of slopes do I have between 12 and 18? Negative, good. Between 18 and 21? Positive. Between 21 and 24? Negative, and then positive. So do these two sign charts give me a window into knowing or being able to look and see when velocity and acceleration are working together? Because that's when it's asking us, is when it's speeding up. Is that right? Speeding up means they have the same signs, okay? So do they have the same sign between 0 and 6? No, but between 6 and 12, they have the same sign. They're both positive, aren't they? And then between 12 and 15, you're writing these intervals. I gotta write these intervals down so I don't forget. What were they? 6 to 12. And then between 12 and 15, are they opposite?
Yeah.
Yes. And then from 15 to 18, they're the same again. And then they're opposite, and then they're the same between 21 and 24. And then they're the same again from 27 to 30. And so those are my intervals. So I'm gonna write those down. Well, actually, you know, I can be really evil and cheat here. I'm sorry. You gotta have fun with technology we can, right? Now those are the intervals. How do we know? Because we have to justify our answers. How did we know? Velocity and acceleration have the same signs. That's how we knew. Yes.
For part C, I'm just a little confused because at 15, the velocity is 0. Why wouldn't acceleration be 0? Like why?
Acceleration is the slope there. The acceleration is the slope to the velocity graph at 15. Its position, the velocity's value is 0, but I'm asking for its rate of change, which is the slope. Okay? All right, so this is a typical kind of question you might see. All right, now let's look at an AP question. Because this is what we're in, is AP.
1969,
I know,
are you sure they have this?
they did. I was a very small child. We went to the moon, didn't we, in 69?
We did.
It's a big year.
With this question?
Yeah. All right, here we go. So this is an AP question from 1969, clearly was non-calculator. A particle moves along the x-axis in such a way that its position at time t is given by this function x equals 3t to the fourth minus 16t cubed plus 24t squared between -5 and 5. Okay, now, inclusive. First thing I do is I circle this because guess what? That's a closed interval, isn't it? It's not negative infinity to infinity. And so I know I'm boxed in there, okay? So part A says, determine the velocity and the acceleration of the particle at time t. Well, how do I find the velocity given the position? You just take the derivative, sure. So then we would say v of t here is equal to, using the power rule, 12t to the third minus 48t squared plus 48t, good. And then it's also asking for the acceleration. So how do we define the acceleration? We just take the derivative of velocity. Using the power rule here, it's going to be 36t squared minus 96t plus 48. Boom, that's 2 points out of 9. We're doing good. All right, part B. At what values of the t, what values of t is the particle at rest? That means the particle isn't moving, so how do we know a particle's not moving?
Velocity zero.
Right, so then I kind of summarize and say, particle is at rest when v of t is equal to 0. And there's my justification, isn't it? In that statement. So I'm going to take the velocity function, v of t, which is equal to 12t cubed minus 48t squared plus 48t, and I'm going to set it equal to 0. Setting that equal to 0 is worth 1 point. And now I'm going to factor out a 12t, and I'm left with t squared minus 4t plus 4, and that's equal to 0. And so 12t times, and this is going to be t and t, and this is going to be 2 and a 2 and a minus and a minus. So this is equal to 0 when t is 0 and 2.
But I feel like multiplicity two.
It does have a multiplicity of 2, but that'll affect us in the next part. Yes. But we don't have to say here, we just know that time equals 2 and at time equals 0, the particle is stopped. So now we're rocking at 4 points probably out of 9. And we're very happy. Part C says, at what values of t does the particle change direction? Now, how do we know when a particle changes direction? It goes from moving right to left or left to right. So what has to happen in the middle of those things? It has to be 0, right? So I need to do a sign chart. So I'm going to do a v of t sign chart. And I know that my velocity goes from -5 to 5. And I'm going to put my zeros on there. What kind of function is your velocity? It's a qubit, right? And its zeros are 0 and 2, and the 2 has a multiplicity of 2, which means if I superimpose its graph,
It bounces.
yay, it bounces to 2. So we're going to do this, pass through, bounces, and up again. All those sign charts in pre-cal and algebra 2 are worth it. Because this is the moment they're most important. So now I know I have a negative velocity, a positive velocity, and a positive velocity. So when, my friends, does this particle change direction? Because right now this is moving left, right, right. The velocity only changes direction or particle, I should say particle only changes direction, excuse me. Particle only changes direction at t equals 0, since v of t changes signs. So what's happening to this particle? It's starting out at -5 somewhere on the x-axis, and it says, okay, I'm moving left until a certain point. At time equals 0, what happens? It stops and says, okay, I'm gonna move right now for 2 seconds. Here we go, we're moving right, and then all of a sudden it says, I'm tired. I'm gonna take a rest for a second, and then do what? Continue going right. So that's what that particle is doing. Okay? Part D. What is the velocity when the acceleration is first 0? So what do we have to find? We have to set the acceleration equal to 0,
And then times it.
then you plug that into the velocity, right? So my acceleration function, you're gonna have to hopefully remember that, is 36t squared
Minus 16
minus 96t
plus 48.
plus 48, and I'm gonna set that equal to 0. Now, I can factor a 12 out for sure. So this is gonna be 12 times, and I'm left with 3t squared minus 8t plus 4 equals 0. And yes, in 1969, this did factor.
3t minus 2.
3t and t
Minus 2 minus 2.
minus 2 minus 2. Yes, that was very nice. So that's going to be when 3t minus 2 is 0, which is 2/3 and 2. So when is the acceleration first equal to 0? At 2/3. So now I need b of 2/3. Now, there's an easy way to do this and a more difficult way. Do we have the velocity in factored form already?
Yeah.
We do, don't we? What was it? I can say v, whoops. V of t was equal to 12t times t minus 2, quantity squared, right? Because we had a multiplicity of 2. And if I want v of 2/3, that's going to be 12 times 2/3 times, well, this is going to be 2/3 minus 6/3 squared. So this is going to be, what is that, 24 over 3, which is 8 times 4/3 squared, which would be 16 times 8 over 9, which is 128 over 9. And did they give us any units here? They don't, so I would say units per time, because they didn't give us any units. So this is v of 2/3. And that would be your answer to part D. All right, so that was an AP example. And that's all I have time for today. So thanks for listening.
Thank you.
And in just a second. Say hi to
There is a
everybody.
camera. Oh.